Hi, this is Dr. Emenaker. In this particular video, we are going to be looking at computing the average rate of change. Okay, so let's take a look at what it means to measure an average rate of change. And then we're also going to look at instantaneous rate of change and discuss the difference between the two of these. An average rate of change is actually something fairly simple. You're accustomed to seeing it. It would be something like 60 miles per hour. Okay, the idea here is that over the course of an hour's time, you will have moved 60 miles. Now, an average rate of change talks about over some period of time or over some distance or something or other, in this case, over an hour's period of time. But the thing to be mindful of is if you're driving down an expressway and you average 60 miles an hour, that doesn't mean that at every moment during that hour you're doing exactly 60. You may wind up behind a slow moving truck and slow down to 50 or 55 and then get around it and be up to 70 or 68 for a while. Average looks at over a period of time, basically what's happening. Instantaneous rate of change talks about at any one moment in time. So let's think about that same trip down the expressway. At one point, you're stuck behind a truck that's doing maybe 45 miles an hour going up a steep grade. Well, you eventually get around the truck, and to try and make up for lost time, you go up to 75 or 78 miles an hour. Now, it could still be the case that over the hour's period of time, you're only averaging 60 miles an hour, sometimes slower than 60, sometimes faster than 60. But ultimately, on average, in an hour's time, you've covered 60 miles. However, when you're trying to make up for lost time and you go past a state trooper who has a radar aimed at you, the trooper is not interested in the part of the time when you're doing 45 and part of the time that you're doing 75 and it averages out to be 60 miles an hour. All they're interested in is at that one moment when they measure your velocity using the radar, it says 75 or 78. Okay, that 75 or 78 is at one specific instant in time, not over an extended period of time. Okay, so that would be an instantaneous rate of change. At that one instant in time, you were measured as or clocked as doing 78 miles an hour. Okay, and regardless how you try and explain that to a judge in court or whatever, that it averages out to 60, you're still paying the ticket for 78 miles an hour. Okay, so we are going to, at a later point, not in this video, but in a later video or class, talk about how do you measure instantaneous rate of change. What we're going to focus on for right now, though, is how do you measure average rate of change? And you already know the formula for the average rate of change. Okay, so if we have an average rate of change, I'm going to abbreviate rate of change as ROC, average rate of change. And what's going to wind up happening here is that this is equal to y2 minus y1 over x2 minus x1. You probably recognize this. This is a slope. Aha. Now, this is going to make things actually pretty easy for us because we've been working with slope you've been working with it since 8th grade or thereabouts. So you're fairly familiar with it. But we could be presented situations like compute the average rate of change. And let's say for y equals x squared plus 1. From, let's go on this from x equals 1 to x equals 3. As we're computing this average rate of change from x equals 1 to x equals 3, let's think about what this really means. We've got a graph. Remember, y squared plus 1 is a parabola that's shifted up 1. And we've got some value here at 1 and some value here at 3. And when we look at the y values, as well as the x values, we get the points. And this line segment that connects those 2 points will give us the rate of change. In other words, it's nothing more than the slope. So to actually compute this, what we're going to do is we're going to compute y1 as being this 1 squared plus 1. And y2 is going to be 3 squared plus 1. Okay, so we're just using the first x value to compute y1 and the second x value to compute y2. Well, the 1 squared plus 1 is going to give us a y value of 2. The 3 squared is going to be 9 plus 1 is 10. To compute this rate of change, also known as the slope, we're just going to take y2, 10, over x2, which is 3, and then do y1, which is 2, and x1, which is 1. So we're really just working with the 2 points where we have the x value is 1, the y value is 2, the x value is 3, and the y value is 10. And we're just doing 2 points like what we would normally do for a slope. And this is going to give us 8 over 2, or a rate of change of 4. Now remember, this 4 is really a fraction. What this says is that y increases by 4 as x increases by 1. So as we move 1 unit to the right, okay, we're going to go up 4 units. And that's really what this rate of change is just telling us, is that for each increase of 1 in the x direction, y is going to increase by 4. Now, because this is a parabola, we need to be mindful that this change won't be the same everywhere. If you take a look at the slope here of a tangent line, that's going to be different from the slope of a tangent line here. The slope, the rate of change, is constantly taking on a different value as we move from one x value to another. For example, let's continue using our y equals x squared plus 1. And in this second case, let's consider x equals 3 to x equals 5. Here, we can compute our y1 using our x value 3 squared plus 1, still using the same equation that we used before, where y equals x squared plus 1. And our y2 value is going to be our x2, which is going to be the 5 squared plus 1. So for y1, we're going to get a value of 10. For y2, we're going to get a value of 26. So we're now working with the points 310 and 526. If we sketch a graph, okay, we're going to have our 3 here, our 5 here, and 1's going to be about there, so it's going to go like this. And what's going to happen this time is our 3 is going to be here, and our 5 is going to be way up here. So what's going to happen this time is the line segment is going to be much steeper. The slope is going to be higher than what it was before. To compute the rate of change this time, our rate of change is going to continue to be y2 minus y1. Our y2s are 26. Our y2 is our y1 is our 10. Our x2 goes with our y2 is going to be 5. And our x1 goes with our y1. So we're going to wind up with this 16 over 2. And in this case, the slope's going to be 8. It's going to be twice as steep as what it was in the previous example. So what this means is that the y value is changing over this second x interval, x equals 3 to x equals 5, the y value is increasing at twice the rate as it was on the interval for x equals 1 to x equals 3. In this case, let's take a look at this second one here. Okay. In this case, our x values changed by 2. We went from x equals 3 to x equals 5. Okay, our change in x, the triangle or the Greek letter delta means change in x, is going to be our 5 minus 3, or it was a change of 2. Now, the amount that x changes can vary. X is also called, or this change in x is also called step size. It's how big of a step are we taking as we move from one x value to another on the graph. In this example we're looking at right now, the step size is 2. We could have gone from something like x equals 3 to x equals 3.1. Here our change in x would have been 3.1 minus 3, which should give us a step size of 0.1. We could also do something like x equals 3 to x equals 3.001. Here our change in x would have been 0.001. The step size can vary from one situation to another or one example to another, just based on how big of a step you take. Now, this delta x, or this change in x, this step size, is abbreviated with the letter h. So anytime we look at how big of a step are we taking, we're going to use the notation h to indicate the step size. Okay, so what does this give us in general terms? In general, we can start out with some x value. And to get the y value, we substitute that x value into whatever our function is. Then we can move some amount to the right or to the left, and we'll have x plus the amount we're moving. And to get the y value, we're going to take that x plus h, that new value, and remember that new value could have been any of these examples or a different example from any of these. It could have been up to 3.1. It could have been up to 3.001. It could have been up to 5. But in each case, the way that we get the y value is by taking whatever this new x value is and substitute it into the function. To come up with a general formula for computing our step size, and then from that, or integrating our step size into computing our rate of change, what we're going to do is we're going to rewrite what we had before. Recall our rate of change was y2 minus y1 over x2 minus x1. We can rewrite this with our y2 value being this. This is going to give us f of x plus h. Now, one of the things that I do when I'm writing slopes is I'll put the y value over its corresponding x value so I don't get things backwards. Okay, so I don't put the wrong x value under the y value. So there we have our f of x plus h, our y value, over our x plus h, that's our x2 value. Then what I'm going to do is I'm going to take the y1 value, this one, and pop that in over here. We're going to have f of x. Similarly, with the x values, I'm going to substitute in my new x value, which is x. This will simplify some, and we are definitely going to go to using the simplified version as we work more and more of these. Notice in the denominator we have x plus h minus x. The x subtracts off, and this gives us this formula that we now have f of x plus h minus f of x over h. This is a really important formula, and in fact, it's called the difference quotient. This is what we're going to use to compute our derivatives, which will start in the next section. Okay. The difference quotient is f of x plus h minus f of x. Notice we're subtracting, that's a difference. And then we're dividing by h. Division is a quotient, subtraction is a difference. Hence, this thing is called a difference quotient. Okay, so let's start out with something fairly straightforward. Let's say we want to compute the difference quotient, and I'm going to abbreviate difference quotient as dq for y equals x squared plus 1. Continuing to work with that same function that we looked at a little bit earlier. Well, recall that the difference quotient is going to be f at x plus h minus f of x all over h. Okay, now sometimes people get a little confused when they look at f of x plus h and are not quite sure what does that mean to do. I'm going to kind of step down to the side here, and I'm going to erase this when I'm done to get it out of the way. But if we want to evaluate f at 2, what we would do is we would take our function x squared plus 1, and we would take and substitute this value of 2 for our x. If we wanted f of 7, we would write our function, saving a space for what we're defining h as, and substituting, or what we're defining x as, and substituting it in there. Okay, to get a little bit more general, suppose we did f of cat. What this would say is to write down the function with a space saved for whatever we're defining x to be. X can be anything. And in this case, we're going to put in the space for x, cat. That's just an illustration to let you, or try and get the idea across that it doesn't matter what you have written here. You just plug it into your function every place there's an x. Okay, now we're going to take this difference quotient one step at a time. The first thing I'm going to do is I'm going to do the easy part. In the denominator, we just have h. It's easy to forget the division by h when you get focused on everything that's going on in the numerator. Now, in the numerator, we're first going to take our function, which is x squared plus 1. And for x, we're going to substitute in x plus h. Minus. And it's really important to have these brackets because we're going to now subtract the whole function, which is x, well, something or other squared plus 1. But in this case, the something or other we want to substitute in is x. And you want to be absolutely sure that you include brackets, parentheses, or something. Because if you do not, this subtraction will not be distributed over every term in that function. And that's a problem. Okay, so what's this going to give us? Well, what we're going to wind up with is we're going to have our h in the denominator. Now, in the numerator, we're going to have x plus h squared. You may know what that equals. You may not be quite sure what that is. One thing is for sure, x plus h squared is not x squared plus h squared. You don't just take and distribute the exponent over the two values. Remember, x plus h squared really means x plus h times x plus h. And what we need to do now is we need to distribute. We're going to take the x times the x times the h times the x, and the h times the h. This is also known as FOIL. You should be familiar with this. And what this is going to give us then, the x times x is going to be an x squared. When we do the x times the h, we're going to get plus xh. Then we're going to do the h plus the x, which is still xh. And then we're going to do the h times the h, which is going to give us h squared. There are a couple of terms we can combine. The 2xh's is going to give us 2xh plus h squared. This is what x plus h squared produces. This is what we're going to substitute in up here. Okay, so what we're going to substitute in is x squared plus 2xh plus h squared. Now we've got to be really careful because remember, when we started out, we did the x plus h squared. That's all of this. However, we still have plus 1. So after we've factored out the x plus h squared, we still need to include our plus 1. Then, in the second part, it's a little bit easier to simplify. It's going to be x squared plus 1. At this point, we can start to subtract common terms. For example, we have an x squared here and an x squared here. When we subtract those cancel out. Notice that we also have a plus 1 here and a plus 1 there. When we subtract those, the plus 1s cancel out. This will leave us then with 2xh plus h squared in the numerator. In the denominator, we have h. All right, so where do we go from here? What we want to do is we want to try and cancel out that h in the denominator. As we move forward, that h in the denominator can be a problem. To get that to cancel, notice that each term in the numerator has a factor of h in it. So what we can do in the numerator is we can rewrite this as h times 2x plus h. And that's all over this h in the denominator. And the nice thing here is since the h in the numerator is times everything in the numerator, and the h in the denominator is times everything in the denominator, and you may say, well, wait a minute, it isn't times anything. It's actually 1 times h. Oh, yeah, so will still be a 1 in the denominator after we cancel. It isn't a 0. And what this gives us then is 2x plus h. Okay, it gives us 2x plus h, but what on earth is 2x plus h? This is our difference quotient. This is what we can use to compute changes, okay, or the rate of change when we know what the step size is. For example, now I'm going to hold on to this. We don't want to lose track of this. Okay. We could compute something like compute the difference quotient using x is equal to 7 and let's say h is 0.1. Okay, so what are we going to do here? Well, we first need to know what f of x is. Let's continue using this f of x equals x squared plus 1. Now we're going to take a look at this a couple of different ways. Well, I don't know. We'll just take a look at it the one way here. First off, notice our 2x plus h is our difference quotient of our original function, x squared plus 1. Okay, so our difference quotient, our formula is this 2x plus h. To compute the difference quotient, our difference quotient is just going to be equal to 2 times the x value, 7, plus whatever h is. This is 0.1. This will give us 14 plus 0.1, or the 0.1. And this will give us a difference quotient of 14.1. Now, what does this mean? This is giving us a slope. Remember, the difference quotient started out way up here. Here we go. Way up at the start, remember, it started out as a slope. So this difference quotient is actually the formula of a slope. And what we're looking at now is the slope as we go from 7. So one of our values would be x equals 7. And our next x value would be 7.1. Okay. And what we're doing here with this difference quotient is we're computing the formula for the slope, and we can look at what the slope's rate of change is if we start at 7 and we take a step size of 0.1. Now what I want to do with the time that we have remaining here is to practice computing a couple of difference quotients. So let's practice computing. We're going to do 2 of them here. Okay, so in our first example, we'll call this example 1, pretty clever, huh? In our first example, let's say we have something like y equals x squared plus 3x minus 4. Okay, we're just asked to compute the difference quotient. We aren't given a value for x, we aren't given a value for h. The idea here is to just get the basic formula. Okay, so what we're going to do here, our difference quotient is f of x plus h minus f of x over h. Pretty soon you'll have this memorized and you won't need to write it down each time. Now, we've got to be really careful because, let me write this in yellow so it doesn't get mixed in with everything else. F of x plus h is going to be, copy down what our function is. It's x squared plus 3 times x minus 4. And then what we're going to do is in each of the places where there was an x, we're going to substitute in what we're defining x to be in this case. We could have called it cat, we could have called it cow, we could have called it dog, but what we're going to wind up labeling it as this time is x plus h. When you are computing what f of x plus h is, it starts out fairly small like this. It's going to expand and get really messy. And then in the end, when we do the subtraction of f of x, things will settle back in and be a lot less complex than what they are looking to be here pretty soon. First off, we've already done what x plus h, the sum squared is. That's x squared plus 2xh plus h squared. Recall, this gives us all of that when we FOIL it out. The next thing I'm going to do is I'm going to distribute the 3 times the x plus h. So that's going to give us plus 3x plus 3h, and then we have the minus 4. Okay, so this is our f of x plus h term. I'm going to set up my difference quotient. I'm going to put my h here. Now, when we insert our f of x plus h, it's this whole thing. That whole thing is going to go in for f of x plus h. So it's going to be x squared plus 2xh plus h squared plus 3x plus 3h minus 4. Then we're going to subtract, and I'm going to put my bracket in before I get focused on what's coming up next. What we want to do here is we want to put in f of x. Well, f of x is nothing more than just saying the y. But the y is the function that we start with. And it'll always be the function that we start with. So this is going to be x squared plus 3x minus 4. All right, so right now we're at the point where, yeah, this is getting pretty messy. However, we are also at the point where we can start subtracting off common terms. For example, we have an x squared here minus an x squared here. The x squareds will cancel when we subtract. Notice next we have a 3x here minus a 3x here. Those will cancel off when we subtract. Now be careful on this next one. We have a minus 4 and minus a minus 4. So that's going to give us a minus 4 plus 4. Aha! Those cancel out as well. After we've got all the cancellation done that we're going to be able to accomplish at this point, we still have our h in the denominator. We're going to have a 2xh. Okay, the 2xh is this first term. Then we're going to have an h squared. And notice we also have a plus 3h. That plus 3h is right here. Be careful, things can kind of blend in with a bunch of stuff that's canceled out and be overlooked. As happened in the previous example, notice every term in the numerator has a factor of h. So I can take and factor an h out of each term in the numerator. And I'm going to have plus h squared plus 3. And that's all over h. Okay, so what I did here was I factored out an h, factored out one of those h's, and an h there, which left us with h times 2x plus h, whoops, not plus h squared, it's going to be plus h, there we go, plus 3. That would have changed things up a bit. Now, notice that we have an h in the numerator times everything in the numerator. We also have an h in the denominator times everything in the denominator. It's really just times 1. We can cancel out the h, and what we're going to have remaining is we're going to have a 2x Now I'm going to swap the h into plus 3. I'm going to put it 2x plus 3 plus h. I could put this over 1, but when you divide by 1, you just get the same thing back, and what's the point of taking the time to write that? Okay, this is now our difference quotient. When we started out with this function, x squared plus 3x minus 4. Let's take a look at a second example. Okay, so I'm going to indicate that this one is solved by putting a little shaded box in next to it, which is a fancy math way of saying that one's done. Okay, on to example 2. Last example we're going to look at in this video. Let's say we have y equals 1 over x. Well, right away, a lot of people are going to say, yeah, that's a problem because we're dealing with fractions. Okay, yeah, it is going to make it a little different, but it'll work. Okay, we're going to compute the difference quotient. Remember, the difference quotient is f of x plus h minus f of x all divided by h equals. Okay, so we're going to have some stuff going on here. F of x plus h is not going to be quite so messy to compute this time. It's going to be 1 over, and then we're going to save a space. Remember, there's an x in the denominator, so I'm saving a space there. And what I'm going to substitute into that space is this x plus h. Okay, that gives us our first term. We're going to have 1 over x plus h minus. Normally we would go with f of x. In fact, right here it is. See it? But f of x is just another way of saying, hey, put in whatever y is. Well, okay, y is going to be 1 over x. Now I want to scoot this first term over a little bit. So I'm going to do 1 over x plus h with a little bit of space there. In the numerator, we now have a fraction minus a fraction. Well, when you have a fraction plus, or in this case, minus a fraction, you have to have a common denominator. The common denominator in this case is achieved by taking the first fraction and multiplying it by the denominator of our second fraction. Here's the denominator of the second fraction. And we've got to be careful here because we don't want to just multiply the denominator by x. What we need to do is we need to include an x in the numerator as well. And the reason for including the x in the numerator is if we multiply by x over x, that's really just a fancy way of saying 1, so we've not changed the first term. Now we're going to focus on our second term here. We want to get the denominator of the second term to also have an x plus h. As we did with the first fraction, I'm now going to multiply the denominator by an x plus h, and that'll give me my x times x plus h in the denominator, but I also need to multiply the numerator by x plus h because x plus h over x plus h is just 1. Anything over itself is 1. So technically we've not changed this second fraction. It's going to look different, but it's still going to have the same value. Okay, so what's going to happen here? I'm going to have my h in the denominator. The first fraction, after I multiply those two together, is going to look like 1 times x. Well, that's going to be x over x times x plus h minus. Then we're going to take, and in our second fraction, we're going to multiply the 1 times the x plus h, and that's going to give us x plus h over, we're going to have the x times the x plus h. What we want to do now is in the numerator, not add, but we want to subtract the two fractions. Before I get into that, remember the denominator is still going to be an h. Now, when I subtract these two fractions, the denominator of those two fractions is still going to be x times x plus h. However, when I subtract, I'm going to have x minus x. The x's will cancel out. Then I'm going to have minus h. Well, that's just going to give me a minus h in the numerator. Okay, so what on earth do we do with this? Well, in the denominator, we have h, but h is really the same thing as h over 1. If you divide by 1, you get the same thing back, h. And what I'm going to do is I'm going to rewrite this. Remember, if you have a fraction, okay, whoops, time to swap the pen. The battery's given out on it, okay. If you have a fraction, and we do have a fraction up here, divided by a fraction, and we do have a fraction down here. When you divide a fraction by a fraction, you may recall this from somewhere back in elementary school, you just invert and multiply. So what we're going to wind up with is a negative h over x times x plus h times, now I'm going to invert the h over 1, and I'm going to get 1 over h. Well, what's this do for me? Well, we have an h here in the numerator, which will cancel with the h in the numerator there. And remember, this h in the numerator is really a negative 1 times h. Okay, so when the h cancels, we still have a negative 1 in the numerator. When we multiply the numerators, that's going to give us this negative 1 times 1. Our numerator is going to be negative 1 over, now in the denominator, this h right here really has a coefficient of 1 on it. So we're just going to take 1 times this. And when you take 1 times the x times x plus h, what you're going to get is x times x plus h in the denominator. This whole deal here is now our difference quotient. Okay, and I can go ahead and put the little shaded square there to say we're done with that one. Now, you can then evaluate different situations like what we talked about up here a ways back. Here we go. Where if you have a given value for your x and a given value for your h. All right, this pretty well finishes up everything that we need to talk about here today with regard to average rate of change. Remember, and this is really important to remember, this difference quotient, whether it be this one or this one, hey, that one looks a lot simpler, doesn't it? Or the one that we came up with earlier, here we go, this one, these are all formulas for slope because a difference quotient is nothing more than a slope. Remember, a difference quotient is nothing more than a slope. And that's really important to keep in mind throughout the entire rest of your history and calculus.